Okay, so I want to solve one of the suggested problems, problem 59, but in the class before that I actually solved problem 50, and that acts as a nice warm-up. So I'll start with that one over here as well. The problem 50, we have an object that's hanging by a string from your rear view mirror while you're accelerating at a constant rate from rest to 28 meters per second in 6 seconds. What angle theta does the string make with the vertical? Okay, so we have our car, we have our rear view mirror, we have an object that's hanging. We're accelerating forward. This acceleration, it makes some angle theta. They're asking for this theta in the problem. And this is our object. This is something I think you'll be familiar with. If you're accelerating forward, the things in the car starts moving backwards. So if you have something hanging from a point, it's just going to slide this way. They don't give you the acceleration, but they give you enough to calculate it. They say that from rest to 28 meters per second in 6 seconds. So delta t is 6 seconds, and your delta v is 28 meters per second. A little bit of kinematics with dynamics. All right, so how does this happen? Now, this is a dynamics problem, so the way I like to start dynamics problems is by a free body diagram. And let's draw a free body diagram. Okay. So I have this object. What forces are acting on it? Well, there is gravity. It's always there. Okay. And what else? Well, there's tension. Okay. The tension is going to act this way. This is going to be theta. So is this. They're all theta. This is tension. And what else? Nothing else. We don't have inertial forces. We don't have fictitious forces. These are the only things. All our forces are contact forces except for gravity. And there's nothing else touching this. This object is hanging here. It's held by a thread. Gravity acts on it. Nothing else can act on it. Okay. Again, we are given the acceleration. So you're in the inertial frame. You don't have fictitious forces. Now, do these cancel? No. They do not cancel. And in fact, they add up to a net force. That net force leads to this acceleration. Okay. And of course, we don't put that net force on the free body diagram. But what we can do is that we can say that, okay, there is no acceleration in this way. So Ft times cosine theta is going to be Fg, which is of course mg. Okay? And then Ft times sine theta, that's the only force acting in the horizontal direction, is going to be m times a being calculated over here. Okay? And now they're actually asking for the angle, and we know the acceleration, we know g, we know everything. How to get this angle from these two? We have two equations for two unknowns, ft as well as theta. Well, if you divide them side by side, ft's go away and you get tangent theta. So tangent theta is going to be, you take this, divide by this. On the left hand side you get tangent theta, on the right hand side you get a over g. Okay, so once you calculate a from there, you can find your tangent theta and you can get your theta. Okay? Now be careful, this is cosine and sine because I took the angle with the vertical. Typically we take the angle with the horizontal, then of course they're replaced. There is no mistake here, I don't think so. But you have to be careful about these things, do not put things blindly. How did I find that this is actually cosine? Because it's the adjacent one. I'm looking for this component, so it does pay to actually, take this angle and carry it over there. Okay? Even with a small tick, just marking the angle would help. All right, so this is just a warm-up for the more complicated problem, problem 59. Let's take a look at that one. Okay. Here we have a surface that's frictionless. We have a large block resting on it. On this, there's another block, and to the corner of it, there's a pulley, and over this pulley goes a rope. This rope goes over. Let's call this theta. It's very small, I know, but there's a very nice figure in the book. This is M, B, and C. We have a setup like this, and we have an external force that's applied in this direction. It's an external force. Determine the formula for the magnitude of the force F exerted on the large block so that the mass MA does not move relative to MC. Ignore all friction, assume MB does not make contact with MC. So it doesn't touch over here, and velocity of A with respect to C is 0. It doesn't slide on this. Now what does this mean? Well, it means they're all accelerating the same way. Okay? In those cases, in those problems, when all your system is a common acceleration, you can actually take your system as a single mass and take all the applied forces, take their vector sum, and then write Newton's law. So this is the only force, only external force that's going to survive. There's gravity, but there's also a normal force, and there's no acceleration this way. The only force acting in this direction is F external. So I can actually write this. F is going to be MA plus MB plus MC times the common acceleration. They are all accelerating the same way. Now, how do we write this? Now, to do that, we have to draw some free body diagrams. And these two are easy. This is a little bit tricky. Okay? I'm going to start with this one. So this is mass A. There is gravity acting on it. It's always there. There is a normal force acting on it. This also happens to be the force on block A arising from C. Okay? And these are actually equal to each other. And we have the tension force. Okay? And this tension force is the only force on mass A that is not cancelling, so this must be MA times this common acceleration, whatever it is. And we can already write this down. So let me write it down this way, because I'll need the space. Now, for this mass B, again, I have gravity, that's always there. This is going to be MB times G. I'm going to have the tension force. Fct, and this must be equal to Fat in magnitude. Their directions are of course different, but their magnitudes are going to be the same, and we actually have this equality. This is Ma times A. Now, these guys do not cancel, and there's going to be some angle theta here, which is going to be the same as this angle over there. So that's from the previous problem. And these do not cancel. In the vertical direction they do. In the horizontal direction they don't cancel. So if I write the cancellation for the vertical direction, I would write Fct cosine theta is equal to Fbg. Right, so I can write this in terms of things that I actually know. Ma times the acceleration cosine theta is equal to mbg. Okay. It's just the same equation, I just plug some numbers in. For the horizontal, they don't cancel. This doesn't have a horizontal component, this one does. It's given by sine theta. So Fct sine theta is going to be mass of this guy times the common acceleration. That's the only force acting on it in that direction. And Fct, as we know, is going to be MAA. A sine theta is MCA. Now we have this equation. And we want to solve for A. If I solve for A, I can put in here. This is two equations for two unknowns. Now, I think the simplest way to solve this will be to square both sides, then add them side by side, and use the identity sine squared theta plus cosine squared theta is equal to 1. Okay? So you square this, add them side by side, and you're going to get MA square A square is equal to MB square G square plus MC square A square. You solve that for A, or A square, and then substitute in there, and you'll get your external force. Now normally, if you didn't have this, you will need to draw a free body diagram for C as well. and then get some equations from there and solve it this way, but in this case you don't need to. And the free body diagram for C is going to be a bit complicated because there's this external force, there's the force from A, there's the normal force, but there's also the force coming from the pulley. And you have to investigate that a little bit more carefully. I'm not going to go into it. I think this is adequate to solve the problem. Perhaps it's solved that way in the solution manual. You can check that out, but I won't do it here.